Climate change refers to long-term shifts in temperatures and weather patterns, mainly caused by human activities, especially the burning of fossil fuels, where they release greenhouse gases into the atmosphere, causing the planet to warm. Therefore, biodiesel has the potential to play a significant role in reducing greenhouse gas emissions, our carbon footprint, and mitigate the adverse effects of climate change. The global annual generation of waste cooking oil is estimated to range from 120 to 220 million metric tons. However, the production of biodiesel from this waste resource has posed significant challenges due to the time-consuming nature of achieving high yields in conventional reactors. In order to address these issues, the utilization of micro-reactor technology has emerged as a potential solution.
Microreactors operate at smaller scale than traditional reactors, handling volumes from microliters to milliliters. Microreactors are engineered for precise control over reaction conditions, including temperature, pressure, and reactant mixing. They promote efficient heat and mass transfer through a high surface-to-volume ratio. This project explores the use of passive and active mixing techniques in Tesla-shaped microreactors to enhance biodiesel production yield. The initial phase focuses on passive mixing, utilizing innovative microreactor geometries to promote mixing through fluid dynamics and diffusion without external energy input. The second phase investigates active mixing, employing ultrasound methods to enhance mixing performance.
In the initial phase of our investigation, 3 distinct geometries inspired by the iconic Tesla shape are conceived and refined for a micromixer and a microreactor devices. These alternative geometries, namely the standard, modified, and obstacle Tesla-shaped configurations, are developed based on a comprehensive analysis of the influence of a fluid flow rate dynamics, pressure drop, and fluid turbulence within the microfluidic channel. The design process employed AutoCAD software to craft the specifications of the 3 alternatives, subsequently enabling their physical realization through fabrication utilizing a CNC machine. The experimental investigation commenced on the 3 microfluidic chips, aiming to examine the impact of varying Tesla-shaped geometries and flow rates of waste cooking oil and methanol on biodiesel yield within the microfluidic system. Computational fluid dynamics simulation using the COMSOL multiphysics software were employed to reinforce and validate the experimental findings.
Let's direct our attention to the concept of active mixing in microreactor. A recent advancement in this field involves the utilization of ultrasound as a novel technology. When reactants are exposed to ultrasound, a considerable number of bubbles are formed. These bubbles subsequently collapse near the interface of immiscible phases, specifically oil and methanol. This phenomenon leads to an increased degree of mixing, resulting in a significant improvement in biodiesel yield. To accomplish our research goal, a sequence of laboratory experiments was conducted. Afterward, the results for the experiments were acquired using gas chromatography (GCMS). Additionally, Manytab software, a robust statistical analysis tool, was employed to ascertain the optimum condition. Our investigation centered around 3 parameters: flow rate, temperature, and ultrasound power.
The initial phase revealed that the modified Tesla-shaped geometry achieved a high mixing index of 99.9% in the micromixer at a high Reynolds number. Additionally, using a potassium hydroxide as a catalyst in the microreactor resulted in a significant maximum biodiesel yield of 94.5%. Moreover, the CFD simulations display strong agreement with the experimental data, enhancing the credibility of studies findings. In the secondary phase, 2 types of experiment was conducted to investigate the influence of acoustic waves on biodiesel production, using a batch-type reactor and ultrasonic device. Yields of 97.5% using sodium hydroxide as a catalyst and 94.8% using a potassium hydroxide as a catalyst were achieved within 13 minutes. In the second set of experiments, utilize a Tesla-shaped microreactor and ultrasonic device biodiesel yield of 99% using sodium hydroxide as a catalyst and 95.7% using potassium hydroxide as a catalyst within 18 seconds only.